The normal distribution. So far, all we've been doing is looking at the numbers of it, right? Like this percentage, that score, all the rest. But so far through this topic, we've actually been dealing with like calculus and stuff, right? And you're like, where's all the calculus gone, right? Well, we haven't been able to deal with any of the calculus because when it comes to this shape, we haven't had anything to integrate. We haven't had the actual function that you can put into an integral, put in boundaries and all the rest, right? So that's what I'm going to unpack for you right now, and it's dealing with this function is what's going to be tomorrow and Friday's lesson, okay? So remember what the probability density function is. This is all stuff from that piece of paper that I gave you the other day, right? These are the three qualities that the probability density function has, and what we're going to try and do is almost like guess who. Like we're going to try and work out what's the function that makes sense of all of this, that has all of these characteristics, right? Now, we have lots of different functions that we've learned. These are all the functions that you learnt about in graphing techniques, plus a little bit more, actually. Like you can graph, with some help, even if you're not very familiar, you can graph all of these, okay? So I want you to have a think about which of these would be closest to something like the probability density function shape that we've been dealing with, the normal distribution, okay? Now, there's a lot to play with here, so I'm going to try and narrow it down for you, okay? Remember how I said this is kind of like guess who, okay? You know how there are some questions that you should ask early on, like is the person male or female, or do they wear glasses, or have they got hair, right? So there are obvious questions to ask. The most obvious question out of these three to look at is this guy right here. You know how it sort of levels off, and then it's got asymptotes horizontally, right? I want you to think about these 6 families of functions and which of them have horizontal asymptotes versus which that don't. Have a think. Okay, so maybe some of you are thinking, okay, which ones do and which ones don't? Do you agree with me that we can really quickly say all of these guys, they're all duds. Do you see that? Polynomials are like straight lines, parabolas, they don't have horizontal asymptotes. In fact, they don't have asymptotes at all. Absolute values are the same. Logs do have asymptotes, but not horizontal ones, they have vertical ones, okay? Trig functions, I mean, you've got sine and cos, they don't have asymptotes. Tan's got asymptotes, but which way do they go? They go up and down. So they're also, yeah, they're vertical, okay? So that leaves us with these two. Rational functions, like something divided by something, and then exponentials. Now think with me, maybe it's been a while since you've had a look at it. Do you remember like rational functions? They look like this. Do you remember? Yeah, the hyperbola, very good, our old friend, okay? Now the problem with every rational function is not only do they have the horizontal asymptotes we want, but, have a look at it, it's also got vertical ones. And this has no vertical asymptotes. Do you see that? Okay. So all that leaves you with is the exponential function. This is the only one we can work with. Except, just look at it for a second, right? It doesn't look anything like this, does it? Right? Well, now, very good, right? So part of it does, but part of it doesn't. Like you've got this part over here, which has that horizontal asymptote behavior. That's the part we want, right? And then you have this right-hand side, you're like, that's no good, right? I don't want the right-hand side to do that skyrocketing thing. Does that make sense? Okay. So how do I fix this? Well, have a look at the x values that work for us. Do you agree that the good x values are the negative ones, right? The negative x values, they're good. The positive ones, no good. What knowledge do we have? What concept do we have that can fix numbers so that they're always positive or negative? What do we call that? We call absolute value, right? Now normally we would say, you put the absolute value signs around it, and what does that mean? Absolute value means always positive. But I don't want the positive side, I want the negative side. So here's what I'm going to do. I'm going to put a minus sign at the front of my absolute value. Are you with me? See what's going on there? Okay, so this is better. It's got that dual asymptote thing, okay? But then you've got a problem. We've solved one problem, but we've created another one, right? Look closely with me. Is this what we want? No. It's not, right? See how it's sharp, right? It's sharp there, and that's no good. We have a name for this kind of point. It's called a cusp. C-U-S-P, okay? Oh, yeah. You're like, I don't want this, okay? I don't want it to be sharp there. I actually want it to be, look at the normal distribution. I want it to be, we have a word for this. It starts with S. What's the, stationary. We want it to be stationary, not sharp, okay? Now, we shouldn't be that surprised that trying a trick like this makes it sharp, because this is what the absolute value of, or negative the absolute value of x looks like. It's sharp, right? So what I want is something that looks like this but isn't sharp. something that's concave down, sort of, right? But it's sort of gentle, right? What do I want that would do that? And the answer is a shape that you guys know, right? An upside down parabola would do that, right? Do you see? It's always negative. That's what we wanted. And also it's gradual there. Does that make sense? So have a look at what happens when we put this guy in the index. Just take a look at that. That's pretty good, right? That's pretty good, okay? Now, hold on. We're not quite done yet. We're not quite done. Because look, we know, just going back to the properties of the normal distribution, that the center, right, the symmetry of it should be where? Think about it. It's on the diagram, right? It should be centered around the mean. Now, this would be fine if your mean was 0, but like your mean's not usually 0, right? It's some other number, okay? What knowledge do we have to be able to move this thing so it centers somewhere else? What would I do? Sean? Okay, there's going to be a constant. Where am I going to put it? I've got to put it with the x, right? Because I want to move it left and right. Does that make sense? So this is what we do. You see how it's the same thing you were looking at before? But you've got that minus mu in there, which moves it over. Does that make sense? Okay, so you're like, aha, now we're talking. Okay? All right, now, stay with me, year 12. Shh. We are almost there, I promise. Okay? This guy here is very close to the normal distribution. The only difference is we don't know how far spread out the thing is or how tall it is. Okay? So just hold on to your hats, and I am going to ask you to pick up your pens at this point, right? In order to take this guy, which is basically the right function, and get the scale right, we have to add in stuff to do with the standard deviation, because that tells you how stretched out this thing is. Okay? So I know it looks gross, but compare it to what we've got here. Okay? This is the real equation. Okay? Now it looks nasty, right? Can you write this down, please? This is essential. In fact, I'm going to write it down too. Shh. Now, we're going to write this down together because I know it looks like a garbled mess, and so we're going to try and make it a little bit better. That's what we're going to do right now. Okay? No. This guy is not on the formula sheet. I will tell you why in a second. Because we never need to use it. But for now, I want to work with this function. Okay. Now the first thing is, let me just go back one slide. Right. You've got it. If you haven't written it off the screen, just write it off the whiteboard. Okay. Oh, I can't go back because I'm recording. Never mind. Okay. The difference between this and what you were just looking at. In fact, I'll write down. Right. The other function we were looking at before looks like this. This is what we were looking at, right? Now just have a look at the difference. I know it looks very scary and intimidating, right? This guy comes into the denominator, right? And then this guy comes out to the coefficient, okay? The key thing I want you to see is it's to do with sigma. It's to do with how spread out your data is, okay? Now, this thing looks gross, so I'm kind of on a mission to simplify it. And we can, because I want you to look closely at the index. Look at that garbled fraction up in there, right? It's not a joke. I wonder if that thing in the index looks at all familiar from what we've been looking at this week. Doesn't it look a whole lot like the equation for a z-score, right? The equation for the z-score is it's x minus mu all divided by sigma, right? Which you've got all the pieces there. So here's what we're going to do, okay? In your book, here's how we're going to simplify this thing, okay? This guy out the front, it just stays put. It's fine. But I want to rewrite this index to make it a little more obvious that I can see the z-score in there, okay? For starters, see how there's a minus and then there's a 2 on the bottom. None of them appear in the z-score formula, so I'm going to pull them out. Okay, so I get this, minus a half, and then you get left with x minus mu squared on sigma squared. Do you agree with that? So I've broken the fraction into 2. It looks gross, but just have a look at the second fraction. Yeah. That's a multiplication, yes. Okay. Have a look at this second fraction. Do you agree that basically I can take out this squared thing, right? The top squared, the bottom squared, so the whole thing is squared. Does that make sense? But look, this guy is, that's the z-score. Right there. That's the z-score, okay? Now, If you haven't written down up to this point, that's okay. Just put your pens down for a second because I'm about to do 3 things all at once and I don't want you to miss them. Okay? I'm going to highlight them all in colors so you can see what's going on. And this is going to be really weird. I'm going to do it right to left because I think that's going to be the most sensible order to do it in. Okay, stay with me. I've got this e to the negative a half, and then I've just said that this is z. Do you agree? That's the formula for the z score. So the first thing that changes is that turns into a z squared. Is that okay? Then, if you have a look in here, have a look at this fraction out the front, right? 1 over, now sigma, right? Standard deviation. Have a look over at my normal distribution. On a z scale, the standard deviation is by definition just 1, right? You see that's the distance from one standard deviation to the next, it's just 1 every time. So instead of writing 1 over sigma this, I can just write 1 over 1 root 2 pi. Does that make sense? You see how I've substituted that sigma over there? Now the last thing I need to do is, see how we started by saying this is a function of x? Oh. This is not a function of x anymore. There are no more x's. What's this a function of? It's a function of z, right? So now I've done all changes. Now you can pick your pen back up again, right? This is the line. In fact, I'm going to write it with proper colors, and I don't need to write this 1. It doesn't change anything, right? Our probability density function we can write as 1 over square root of 2 pi e to the negative 1 onto z squared. I know it's still not beautiful or simple, but it's better. It's better than what we started with, okay? And this really will be the version that we use going forward, okay? Because it's better than that guy, all right? Now, I know this looks terrible, okay? But I want to give you...
You have to find the beauty in it.
Well, this is the thing, right? Here's my pitch for you, okay? In 2 minutes or less. This is beautiful because it fits every single thing that we wanted about the normal distribution. It's got the symmetry, it's got the right location, it's got the right size. Even though it is complicated, it does everything I want it to, okay? The only catch is, when you have a look at this guy, right? What do we generally do with probability density functions? Like, how do I find a probability? How do I find variance? What's the thing I do after this? I integrate, right? I integrate. Now, if you look at this and think, gross, I don't want to integrate that, then that's the right instinct, because I'm going to show you what happens if you integrate. The probability density function, what do we call it when you integrate the PDF? You get the, do you remember? The CDF, the cumulative distribution function. Don't write this down, don't panic, but this is the cumulative distribution function, okay?
Why would you show me that?
Now I'm showing it to you because, thankfully for us, we never ever need to use this, okay?
I'm excited. Why is there an exclamation mark?
You're wondering why there's an exclamation mark there. It's a piece of mathematical notation,
No, it's not.
okay? It's called the factorial. It's called the factorial, okay? Now, we're right on the bell. So over the next 2 days, Thursday, Friday, what we're going to do is, since we don't want to do this, what's the alternative? There are 3 alternatives, and that's what we're going to do on Thursday and Friday.